Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good day to everyone. For this week, we will be discussing on chapter 10 on the characteristics, processing and applications of polymers. We have now come to the second part of the chapter that is focusing on the discussion in terms of the crystallinity of polymers and the properties of polymers, that is emphasizing on the thermal and mechanical properties of polymer. The last part on the structure of polymer is about the crystallinity in polymers. We have mentioned previously that polymers are either crystalline or semicrystalline or amorphous. So when we talk about crystallinity, they are the ordered atomic arrangement which involve molecular chains, and the crystal structures are in terms of the unit cells, which you have already discussed in chapter 3 of this course. One example given here is the polyethylene unit cell. This example shows the crystalline region in polymers. We can observe thin platelets with chain folds at the faces of these crystalline polymers, and the chain are folded together in this structure. So crystallinity in polymers. In actual fact, polymers are rarely 100% crystalline, and therefore it is difficult for all regions of all chains to become aligned. So as we can see from the illustration of this slide, there are some degree of crystallinity which is expressed as percent of crystallinity. So here we can see the crystalline, the amorphous, and semicrystalline region in between them. So some physical properties depend very much on the percent of crystallinity, and heat treating causes crystalline regions to grow and the percent of crystallinity to increase. This slide gives you an idea of how single crystal forms, and it is only able to be observed if its slow carefully grow. Again, on the crystalline polymer, if we observe clearly on the crystalline side, we may observe what we call the spherulites, which is fast growth, and they form layered structures or what we call laminal structures. I'm sure by now you're familiar with the word lamella, which you have already learned in chapter 7 in phase diagram. So for polymers, we can see here the nucleation site of polymer materials and the direction of the crystal growth. So this one here is the lamellar chain folded crystallite, and in between them we have the amorphous material and the Ti molecule. And we have this boundary that is called the interspherulitic boundary between them. The slide here gives you a TM image of spherulites, which is a cross polarizes. Here we can see a beautiful picture of the spherulites in actual imaging, and it has this Maltese cross between them. We have now come to the second part of polymer aspects, that is on the properties of polymer. Let's now begin with the thermal properties of polymer. The two important thermal properties when we want to characterize polymer materials is in terms of the melting temperature and the glass transition temperature. Now that you are aware that polymers can be either fully crystalline, which is very uncommon, or semi-crystalline, like the one in this green plot, or fully amorphous or non-crystalline material, like the one plotted in this red line and labeled as A, for the semi-crystalline labeled as B, and the fully crystalline labeled as C. For completely crystalline material, they have only the melting temperature. But uniquely, for the semi-crystalline polymer materials, which is majority of the polymers, they have both the TG or the glass transition temperature and the Tm, which is the melting temperature. And for the non-crystalline material, like glass, they only have what we call the glass transition temperatures. So what factors affect the melting temperature and the glass transition temperature? Both Tm and Tg increase with increasing chain stiffness. And this chain stiffness, they are increased by the presence of bulky side groups, polar groups or side groups, and the chain double bonds and aromatic chain groups. And the boiling temperature, or the Tm, increases with the increase of molecular weight. And the regularity of repeat units affects only the melting temperature. So clearly we can see that the properties of these polymer materials are greatly affected by the structure of the polymer molecules as well as the bonding between them. The second aspect when we talk about the properties of polymers is in terms of the mechanical properties. Here on this slide, we are looking at a plot of stress-strain curve for three different types of polymers which we have classified at the beginning of the chapter. We have the brittle polymer, the plastic, and the elastomer. So typically, the brittle polymer is for those from the thermoset groups, and the plastic one refers to the thermoplastic material, and for the elastomer, as we know, they are super elastic material and they can resist very, very low strength or stress level as compared to the plastic material, which is more ductile, or of course the most stiffest and the strongest material of the three, that is the thermoset materials. So the fracture strength of polymers is about 10% of those for metals. They are very, very poor on their own. Unreinforced polymers are relatively very, very weak compared to metal or ceramics. Deformation strains for polymers, however, are greater than 1000%. And compared to metals, most metals deform less than 10%. So that is the major difference between the mechanical properties of polymers with metals, for example. For the mechanism of deformation, let's first talk about the semicrystalline or plastic polymers. We can see the different plots for brittle failure, plastic failure, and this is the onset of necking for this particular plot of semicrystalline polymers. And this is the range for unload and reload. So at initial state, the undeformed structure has this semicrystalline polymer looking like. At a point here, there is a amorphous region that is elongating. At this maximum or at the onset of necking, the crystalline regions are becoming aligned. And the crystalline block segments are separated at almost failure. And when it achieves the plastic failure, we have the fibrillar structure at the near failure point. Now, let us compare that with the brittle cross-linked polymer as well as the network polymer. Now, first thing first, the cross-linked polymer. This is what happened at the initial state and how the cross-linked polymer looks like. And that is at the near failure, how the cross-linked polymer have changed or deformed. If we compare that with the initial state of network polymer, at this point, this is how we can illustrate the network polymer behavior. And lastly, at the near failure, this is how the network polymer behaves at the end of the deformation. Lastly, let's compare with the mechanism of deformation for elastomer materials. At initial state, the amorphous chains are king and cross-linked. When they undergo large deformation. The deformation is reversible. And lastly, at the point of failure, the chains are straighter but they are still cross-linked. So we can compare the elastic behavior of elastomers with those of the brittle behavior of aligned, cross-linked and network polymers, as well as the plastic behavior or ductile behavior of semicrystalline polymers, as shown on previous slides.